Hello everyone. Today we are going to analyze this beam using Kani's method. Before analyzing, let us see the beam one time. In this beam, there are three spans: span AB, span BC, and span CD. Also, there is a overhanging span DE. In the span AB, there is a point load 40 kN acting in the center. In the span BC, there is a concentrated moment 80 kN/meter. It is acting in the clockwise direction. In the span CD, there is uniformly distributed load 48 kN/meter acting for the full span. In the overhanging span DE, there is a point load 40 kN acting in the point E. The moment of inertia for the span AB is 3I. The moment of inertia for the span BC is 2I. For the span CD, it is 2I, and for the overhanging part, it is I. AB and BC are 4 meter long. CD is 5 meter long. The overhanging part is 3 meter long. In this beam, there are 7 moments we have to find. In the point A, there is a fixed support. In the fixed support, there will be a moment. Here, the moment is MAB. In the joints, there will be 2 moments. In the joint B, there are 2 moments, MBA and MBC. In the joint C, there are 2 moments, MCB and MCD. And in the joint D also, there are 2 moments, MTC and MDE. So totally we have to find 7 moments. Also, we have to find 4 vertical reactions, RA, RB, RC and RD. In the joint D, we can easily find the final moments because on the right of D, there is overhanging. To calculate MDE, we have to multiply the point load 40 kN with the overhanging distance 3. When we do that, we are getting 120. MDE is acting in the anti-clockwise direction, so it should be negative. In this case, we have to apply a negative sign with the load so that we will get a negative moment. The values of MDC and MDE will be same, but they will have the different signs. MDE is acting in the anti-clockwise direction. It should be negative. MDC is acting in the clockwise direction, so it should be positive, but both of them will be having the same value. In this concept, we can calculate MDC very easily. For that, we have to just change the sign of MDE. When we do that, we are getting positive 120. Now, let us calculate the fixed end moments. First, let us find them in the span AB. In the span AB, there is a point load 40 kN acting in the center. The formulas for the fixed end moments are minus WL upon 8 and positive WL upon 8. Using the formulas, we are getting M of AB and M of BA. Now let us take the span BC and find out the fixed end moments. In the span BC, there is a concentrated moment 80 kN/meter acting in the clockwise direction. This moment is acting in the center. The formulas for the fixed end moments are positive M upon 4 and positive M upon 4. Using the formulas, we are getting M of BC and M of CB. Now let us make the fixed end moments in the span CD. In the span CD, there is UDL 48 kN per meter and it is acting for the full span. The formulas for the fixed end moments are minus WL square upon 12 and positive WL square upon 12. Using the formulas, we are getting M of CD and M of DC. We have calculated the fixed end moments in the spans AB, BC and CD. No need to make the fixed end moments in the overhanging span. Now let us make the adjusted fixed end moments. Let us make a table. In the table, first let us enter all of the members. Then let us enter the fixed end moments. In the joint D, we have calculated the final moments MDC and MDE. Let us apply the value of MDE here. The final moment for DC, MDC is 120. So we have to make DC 120. For DC, the fixed end moment is 100. When we add 20 with this 100, we will get 120. So we have released DC and we have to give the carryover from DC to CD. The carryover should be done in the same way we did in the moment distribution method. When we divide 20 by 2, we will get 10. Now let us calculate the adjusted fixed end moments for AB, BA, BC and CB. There are no changes. For CD, we have to add these two values. After adding, we are getting minus 90. In the Kani's method, we have to find the rotation factor. To find the rotation factor, we have to calculate the stiffness. We have to calculate the stiffness only in the joints. There are three joints, joint B, joint C and joint D. No need to calculate the stiffness in the joint D because there is overhanging on the right of D. Only we have to calculate the stiffness in the joints B and C. Let us see the formulas to find out the stiffness. If the fair end is fixed, the formula is 4EI upon L. If the fair end is hinged or with roller support, the formula is 3EI upon L. If the fair end is continuous, the formula is 4EI upon L. Now let us calculate the stiffness values. First, let us calculate in the joint B. From the joint B, we have to calculate two stiffness values. Stiffness for BA and stiffness for BC. First, let us calculate for BA. For that, from the point B, we have to look at the point A. In the point A, we are having a fixed support. If the parent is fixed, the formula is 4EA by L. The length of AB is equal to 4 meter. We can apply. The moment of inertia is 3I. So instead of I, we have to apply 3I. Finally, we are getting 3EI. Now let us calculate for BC. For that, from the point B, we have to look at the point C. The point C is continuous because after the point C, we are having a span CD. If the parent is continuous, the formula for stiffness is 4EA by L. The length of BC is equal to 4 meter. We can apply. The moment of inertia is 2I. So instead of I, we have to apply 2I. Finally, we are getting 2EI. Now let us calculate the stiffness values from the joint C. From the joint C, we have to calculate two stiffness values for CB and for CD. First, let us calculate for CB. For that, from the point C, we have to look at the point B. The point B is continuous because after the point B, we are having a span AB. If the parent is continuous, the formula is 4EA by L. The length of BC is equal to 4 meter. We can apply, and the moment of inertia is 2I. So instead of I, we have to apply 2I. Finally, we are getting 2EI. Now let us calculate the stiffness for CD. For that, from the point C, we have to look at the point D. In the point D, we are having a hinged support. If the parent is hinged, the formula is 3EI by L. The length of CD is 5 meter and the moment of inertia is 2I. We can apply. After that, we are getting 1.2 EI. We have to be very careful. We cannot consider the point D as continuous because after the point D, we are having overhanging span. Now, let us calculate sigma k, that is summation of stiffness. In the joint B, we have calculated two stiffness values. We can add both of them. After adding, we are getting 5 EI. In the joint C, we have calculated two stiffness values. We can add both of them. After adding, we are getting 3.2 EI. Now, let us calculate the rotation factor. The formula for rotation factor is here, minus 1 by 2 into k by summation of k. We have already calculated the values of k and the summation of k. We can apply in the formula. For BA, the rotation factor is minus 0.3. For BC, the rotation factor is minus 0.2. For CB, the rotation factor is minus 0.3125. And for CD, the rotation factor is minus 0.1875. In Kani's method, we have to make boxes like this in the joints. We are making the boxes in the joint B and in the joint C. No need to make the box in the joint D because we have already calculated the final moments in the joint D and we have released it. So only make the boxes in the joint B and in the joint C. We have to enter the fixed end moments inside the boxes. In the point A, there is only one fixed end moment, that is MAB. In the point B, there are two fixed end moments, MBA and MBC. In the point C also, we have made two fixed end moments, MCB and MCD. In the point D, we have already calculated the final moments, so there is no need to enter the moments. Now let us add the fixed end moments in the joints. In the joint B, we are having two fixed end moments. We can add both of them. After adding, we are getting 40. In the joint C also, we are having two fixed end moments. We can add both of them. After adding, we are getting minus 70. Now we have to enter the rotation factors. In the joint B, we have calculated two rotation factors for BA and for BC. For BA, it is minus 0.3 and for BC, it is minus 0.2. In the joint C also, we have calculated two rotation factors. For CB, it is minus 0.3125. For CD, it is minus 0.1875. Now we are going to calculate the rotation contributions. The rotation contributions will be available only in the joints. We are having three joints, joint B, joint C and joint D. In the joint D, we have already calculated the final moments and we have released it. So in the joint D, the rotation contribution is 0. In this case, we have to make the rotation contributions only in the joints B and C. In the joint B, we are having two rotation contributions, M-BA and M-BC. In the joint C also, we are having two rotation contributions, M-CB and M-CD. Let us see the formula to calculate the rotation contribution. Summation of rotation contributions at parent plus summation of fixed end moments into the rotation factor. Let us see how to calculate the rotation contributions using the formula. First, let us see how to calculate M-BA. M-BA is located in the point B. For the point B, the fair ends are the point A and the point C. In the point A, the rotation contribution is 0 because in the fixed support there will be no rotation contribution. From the point C, we have to choose M-CB. So, for the summation of rotation contributions at the fair end, we are having 0 plus M-CB. The summation of fixed end moment is 40. The rotation factor for BA is minus 0.3. In this way, we can calculate M-BA. Now, let us see how to calculate M-BC. M-BC is located in the point B. For the point B, the fair ends are the point A and the point C. In the point A, the rotation contribution is 0 because it is fixed. From the point C, we have to select M-CB. So, for the summation of rotation contributions at the fair end, we are having 0 plus M-CB. The summation of fixed end moment is 40. The rotation factor for BC is minus 0.2. We can see that for M-BA and M-BC, all the values are same except the rotation factors. Now let us see how to calculate M-CB. M-CB is located in the point C. For the point C, the fair ends are B and D. From the point B, we have to select M-BC and the rotation contribution in the point D is 0 because we have already released it. So, for the summation of rotation contributions at the fair end, we are having M-BC plus 0. The summation of fixed end moment is minus 70. The rotation factor for CB is minus 0.3125. In this way, we can calculate M-CB. Now, let us see how to calculate M-CD. M-CD is located in the point C. For the point C, the fair ends are the point B and the point D. From the point B, we have to select M-BC and the rotation contribution in the point D is 0. So, for the summation of rotation contributions at the fair end, we are having M-BC plus 0. The summation of fixed end moment is minus 70. The rotation factor for CD is minus 0.1875. In this way, we can calculate M-CD. You can see that for M-CB and M-CD, all the values are same except the rotation factor. Now let us calculate the rotation contributions in the joint B. First, let us calculate M-BA. In the point A, the rotation contribution is 0 because it is fixed. In the point C also, M-CB is 0 because initially there will be no rotation contribution. So, for the summation of rotation contributions at the fair end, we are having 0 plus 0. For the summation of fixed end moments, we are having 40. The rotation factor for BA is minus 0.3. After calculations, we are getting M-BA is equal to minus 12. We know that M-BA and M-BC will be having the same values except the rotation factor. The rotation factor for BC is minus 0.2. We can apply. Finally, we are getting minus 8. We can enter the value of M-BA here and M-BC here. Now let us calculate the rotation contributions in the joint C. First, let us calculate M-CB. The rotation contribution in the point B is minus 8 and the rotation contribution in the point D is 0. So, for the summation of rotation contributions at the fair end, we are having minus 8 plus 0. The summation of fixed end moment is minus 70. The rotation factor for CB is minus 0.3125. After the calculations, we are getting M-CB is equal to 24.375. We know that for M-CB and M-CD, all the values are same except the rotation factor. The rotation factor for CD is minus 0.1875. After the calculations, we are getting m dash CD is equal to 14.625. We can enter the value of m dash CB here and the value of m dash CD here. So we have made the first cycle. Let us start the second cycle. Now let us start the second cycle. First, let us calculate m dash BA. In the point A, the rotation contribution is 0. In the point C, now we are having the rotation contribution, that is 24.375. So for the summation of rotation contributions at the far end, we are having 0 plus 24.375. The summation of fixed end moments is 40. The rotation factor for BA is minus 0.3. We can apply. After the calculations, we are getting m dash BA is equal to minus 19.312. We know that for m dash BA and m dash BC, all the values are same except the rotation factor. The rotation factor for BC is minus 0.2. After the calculations, we are getting m dash BC is equal to minus 12.875. We can enter the value of m dash BA here and m dash BC here. Now let us calculate m dash CB. The latest rotation contribution in the point B is minus 12.875. In the point D, the rotation contribution is 0. So for the summation of rotation contributions at the far end, we are having minus 12.875 plus 0. The summation of fixed end moments is minus 70. The rotation factor for CB is minus 0.3125. After the calculations, we are getting m dash CB is equal to 25.898. We know that for m dash CB and m dash CD, all the values are same except the rotation factor. The rotation factor for CD is minus 0.1875. After the calculations, we are getting m dash CD is equal to 15.539. We can enter the value of m dash CB here and we can enter the value of m dash CD here. So we have finished the second cycle. Let us move to the third cycle. First, let us calculate m dash BA. The rotation contribution in the point A is 0. The rotation contribution in the point C is 25.898. So for the summation of rotation contributions at the far end, we are having 0 plus 25.898. The summation of fixed end moments is 40. The rotation factor for BA is minus 0.3. We can apply. Finally, we are getting m dash BA is equal to minus 19.769. The rotation factor for BC is minus 0.2. We can apply. Finally, we are getting m dash BC is equal to minus 13.18. We can enter the value of m dash BA here and m dash BC here. Now let us calculate m dash CB. The latest rotation contribution in the point B is minus 13.18. The rotation contribution in the point D is 0. So for the summation of rotation contributions at the far end, we are having minus 13.18 plus 0. The summation of fixed end moment is minus 70. The rotation factor for CB is minus 0.3125. After the calculations, we are getting m dash CB is equal to 25.994. The rotation factor for CD is minus 0.1875. After the calculations, we are getting m dash CD is equal to 15.596. We can enter the value of m dash CB here and m dash CD here. We have finished the third cycle. Let us move to the fourth cycle. The fourth cycle should be made in the same way we did the previous cycles. You can see the calculations here. Now we can stop because in the third and fourth cycle all the values are approximately equal. So we can stop now and find the final moments. To calculate the final moments, we have to apply this formula. Fixed end moment plus 2 into rotation contribution at near end plus rotation contribution at the far end. Let us make one table. In the table, we can enter the fixed end moments 2 into near end contributions, far end contributions, and the final moments. We have already calculated the fixed end moments. We can enter them. For the near end contribution and far end contributions, we have to select the values which we got in the final cycle. For AB, the near end contribution is 0, so 2 into 0. For BA, the near end contribution is minus 19.8. For BC, the near end contribution is minus 13.2. For CB, the near end contribution is 26. For CD, the near end contribution is 15.6. Now let us enter the far end contribution. For AB, the far end is BA. In BA, the contribution is minus 19.8. For BA, the far end is AB. In AB, the contribution is 0. For BC, the far end is CB. In CB, the contribution is 26. For CB, the far end is BC. In BC, the contribution is minus 13.2. For CD, the far end is DC. In the point D, there is no contribution because we have already released it, so 0. Now we can add these three values and get the final moments. For DC, we have to be very careful. We cannot add the near end contribution and the far end contribution because we have already released it and got the final moment. So in this problem, we have calculated all the moments. In this analysis, we have calculated all of the moments. For MAB, we got a negative value. That means it is acting in the anti-clockwise direction. For MBA, we got a negative value. So it is also acting in the anti-clockwise direction. For MBC, we got a positive value. That means it is acting in the clockwise direction. Previously, we assumed that MBA would be acting in the clockwise direction and MBC would be acting in the anti-clockwise direction, but our assumptions are wrong. For MCB, we got a positive value. That means it is acting in the clockwise direction. For MCD, we got a negative value. That means it is acting in the anti-clockwise direction. Now let us find the vertical reactions. First, let us take the span AB and calculate the vertical reactions. In the span AB, there are two moments, MAB, which is acting in the anticlockwise direction, and MBA, which is also acting in the anticlockwise direction. First, I am going to find out RA. For that, I am going to take moment about B. In this case, I am moving towards right hand side. Clockwise will be positive and anticlockwise will be negative. RA is acting towards the point B in the clockwise direction. So it will be positive and the distance is 4 meter. So for RA, the point load 40 kN is acting towards the point B in the anticlockwise direction, so it will be negative and the distance is 2 meter. Then we have two moments, both of them are acting in the anticlockwise direction, so both of them will be negative. Finally, we are getting RA. By applying the rule sigma V is equal to 0, we can find out RB1. Now let us take the span BC and find out the vertical reactions. In the span BC, there are two moments, MBC, which is acting in the clockwise direction, and MCB, which is also acting in the clockwise direction. In this span, first I am going to find out RB2. For that, I am going to take moment about C. RB2 is acting towards the point C in the clockwise direction. So it will be positive and the distance is 4 meter. So for RB2, the concentrated movement is acting in the clockwise direction. So it will be positive. Then we have two end movements, 19.6 and 58.8. Both of them are acting in the clockwise direction. So both of them are positive. Finally, we are getting RB2. For RB2, we will get a negative value. That means our assumption is wrong. We assumed that RB2 is acting upwards, but actually it is acting downwards. Now let us apply the rule sigma v is equal to 0 and find out RC1. Here we have to be very careful. When we apply the value of RB2, we must apply as negative value because it is acting downwards. Finally, we are getting RC1, which is equal to 39.6 kN. Now let us take the spans CD and the overhanging span DE together and find out the vertical reactions. When we take these spans together, no need to consider MDC and MDE because they will get eliminated. Only we have to consider MCD, which is acting in the anticlockwise direction. When we take moment about D, we can find out RC2. Then we can apply the rule sigma V is equal to 0 and find out RD. Now let us add RB1 and RB2 so that we will get RB. For RB, we will get a negative value. That means RB is acting downwards. Then let us add RC1 and RC2. After adding, we are getting RC. Now we are going to draw the shear force diagram. I am going to calculate the shear force values from the point A. In this case, I am moving towards right hand direction. Upwards will be positive and downwards will be negative. You can see the shear force values. Using the values, we can draw the shear force diagram. Now let us draw the free movement diagram. For drawing the free movement diagram, we have to consider every span as a separate simply supported beam and calculate the bending moments. First, let us take the span AB. In the span AB, there is a point load acting in the center. If in the simply supported beam, point load is acting on the center, the formula for calculating the maximum bending moment is WL upon 4. Using the formula, we are getting 40. In the span BC, there is a concentrated moment. The concentrated movement is acting in the center and it is acting in the clockwise direction. The formulas to find out the maximum bending moments are m upon 2 and m upon 2. Here the moment is 80, so 80 by 2 we will get 40. On the right of the moment it will be positive and on the left side it will be negative. Now let us take the span CD. In the span CD, there is UDL 48 kN per meter acting for the full span. The formula to find out the maximum bending moment is WL square upon 8. After applying the values inside the formula, we are getting 150. For the point load and for the point movement, the free movement diagram will be in the shape of triangles. For the UDL, the free movement diagram will be in the shape of parabola. Now let us make the end movement diagram. In the direction of the movements, we have to make the diagram. If the end movement diagram comes above this line, that will be negative. If it goes below the line, that will be positive. So here and here it is negative and here it is positive. Now we can combine the free movement diagram and end movement diagram so that we will get the bending moment diagram. Now we are going to end this session. Thank you for watching this video.